What makes jet engines strong or hip replacements reliable? Often, it's titanium, element number 22, the superhero of metals. It's as strong as steel but only half the weight, making it perfect for building tough, lightweight structures. Titanium is also highly resistant to corrosion. Even salt water barely affects it. This makes it ideal for ships, submarines, and medical implants, thanks to its biocompatibility. But titanium isn't just lying around, it's locked in minerals deep in the Earth's crust. Extracting pure titanium is complex and energy-intensive, which is why it's pricier than steel or aluminum. In this journey, we'll follow titanium from the ground to high-tech machines and medical marvels. We'll see how it's mined, purified, and shaped into everything from airplane wings to bicycle frames. So put on your safety goggles, let's dive into the science of titanium. If you went searching for pure titanium in the wild, you'd be out of luck. Unlike gold or copper, titanium never appears in its pure, shiny form in nature. Instead, it's cleverly hidden away inside tough minerals like ilmenite and rutile. These minerals are the secret vaults where nature stores its titanium, locking it up in a chemical form that's hard to extract. Ilmenite is a black, heavy mineral, while rutile is reddish-brown and needle-like. Both are rich in titanium, but you'd never guess just by looking at them. Over millions of years, wind and water erode rocks containing these minerals, washing them down rivers and streams. Eventually, they settle in coastal sands, especially on beaches with dark, heavy mineral layers. These black sands might look ordinary, but they're actually treasure troves packed with valuable titanium-bearing minerals. To get at these hidden riches, miners use a technique called dredge mining. Imagine giant floating vacuums gliding across the water, sucking up sand and silt from the bottom. These machines can process huge amounts of sand every day, making it possible to collect enough mineral-rich material for further processing. The sand and water mixture, called slurry, is pumped to a nearby processing plant. Here, a series of clever physical methods are used to separate the heavy minerals from the lighter sand. It's a bit like panning for gold, but on a massive industrial scale. Spiral concentrators use gravity to sort out the denser ilmenite and rutile from the lighter grains of sand. Magnets are then used to pull out the weakly magnetic ilmenite, leaving behind a concentrate that's rich in titanium minerals. This process is both efficient and environmentally conscious, minimizing waste and maximizing recovery. After all this sorting and separating, what's left is a concentrate packed with titanium dioxide, known as TiO2. This white, powdery substance is the starting point for almost everything titanium-related. The vast majority of this TiO2 doesn't become metal. Instead, it's transformed into a brilliant white pigment used in paints, toothpaste, sunscreen, and even the paper we write on. Its brightness and opacity make it an essential ingredient in countless everyday products. Only about 5% of the world's titanium dioxide goes on to become the metal itself. That's a tiny fraction, but it's where the magic really happens, turning a humble mineral into one of the most remarkable metals on Earth. The journey from sand to shining metal is just beginning at this stage. The concentrate is transported for further processing, where it will undergo even more complex transformations. Mining and mineral separation are just the first steps in unlocking titanium's full potential. Each stage requires precision, expertise, and advanced technology to ensure the highest quality output. But the real transformation, the one that turns white powder into a superhero metal, happens in the next stage, where chemistry takes center stage. Here, powerful chemical reactions break the bonds that hold titanium captive in its mineral form. From ancient rocks buried deep in the earth to cutting-edge aircraft, medical implants, and sports equipment, titanium's story is one of discovery, innovation, and human ingenuity. Its journey mirrors our own quest to unlock the secrets of the natural world. Next, we'll follow the incredible transformation as this ordinary-looking white powder is turned into a metal with extraordinary properties. Strong, light, and nearly indestructible. So let's dive into the fascinating world of chemistry and see how titanium is finally set free from its mineral prison. Turning titanium dioxide into metal is where the real magic of modern metallurgy happens, and it all centers around a remarkable method known as the Croll Process. This process is the backbone of titanium production worldwide, transforming a common mineral into one of the most valuable metals on Earth. The journey begins with titanium dioxide, or TiO2, a white powder found in minerals like rutile and ilmenite. To start, TiO2 is heated and reacted with chlorine gas and carbon at extremely high temperatures inside specialized furnaces. This intense reaction produces titanium tetrachloride, or TiCl4, a colorless, volatile liquid. During this step, oxygen atoms are swapped out for chlorine, resulting in a liquid compound that can be easily separated from impurities. The TiCl4 is then carefully purified by distillation, a process that removes unwanted elements and ensures the highest possible quality for the next stage. Purity is absolutely crucial at this point. Any lingering impurities can make the final titanium product brittle and weak, undermining its legendary strength and corrosion resistance. Once purified, the TiCl4 is pumped into a sealed reactor vessel where it meets molten magnesium. This is where the real transformation takes place. At temperatures soaring above 1000 degrees Celsius, the magnesium acts as a powerful reducing agent, grabbing the chlorine atoms and leaving behind pure titanium. The result is a spongy, porous mass known as titanium sponge. This titanium sponge is the very first solid form of the metal, and it marks a major milestone in the process. It's light, strong, and ready for further refinement. The Croll process is slow and incredibly energy-intensive, requiring careful monitoring and vast amounts of electricity. But despite these challenges, it's the essential key to unlocking titanium's unique properties and making it available for high-tech applications. From a humble white powder to a metallic sponge, chemistry and engineering work hand in hand to transform titanium into a material that can change industries. But the journey doesn't end here. The next challenge is to turn this rough sponge into usable, high-purity metal that can be shaped and formed for real-world use. This involves additional purification and melting steps, where the titanium is further refined and cast into solid ingots, ready for manufacturing. Let's follow the next steps and see how this extraordinary metal is finally prepared for the real world, ready to be used in everything from airplanes to medical implants. After the Croll process, we're left with a unique mixture: titanium sponge and magnesium chloride. The titanium sponge is a porous, gray material that looks almost like a metallic sea sponge, while the magnesium chloride is a byproduct of the chemical reaction. Both are collected in large industrial containers, ready for the next stage of processing. The magnesium chloride doesn't go to waste. It's carefully recycled and reused in future batches, making the process more sustainable and cost-effective. Meanwhile, the titanium sponge undergoes a crucial purification step. It's placed in a high-tech vacuum chamber where any remaining impurities, such as excess magnesium or chlorine, are removed under intense heat and low pressure. This purification ensures that the titanium reaches an impressive level of purity, often exceeding 99%. Technicians meticulously inspect the purified sponge, confirming it's ready for the next transformation. At this stage, the titanium is almost ready to become a usable metal. The purified sponge is then pressed into dense blocks, which are loaded into a vacuum or inert gas furnace. This environment is essential to prevent the highly reactive titanium from absorbing oxygen or nitrogen, which could weaken the final metal. The next step is vacuum arc remelting, or VR. Here, a powerful electric arc melts the titanium block, causing it to drip and solidify in a water-cooled copper mold. This process not only shapes the metal, but also helps remove any lingering impurities. To achieve the highest quality, this melting process is often repeated several times. Each cycle helps ensure the titanium structure is uniform and free from internal defects, making it strong and reliable for demanding applications. The result is a massive, glowing ingot of pure titanium, carefully extracted from the furnace and allowed to cool. These ingots can weigh hundreds of kilograms and are the foundation for all titanium products. In vast warehouses, rows of these titanium ingots are stacked and stored, awaiting further processing. Each ingot represents the culmination of complex chemical and physical transformations. The journey from a brittle, porous sponge to a solid, gleaming ingot is now complete. This transformation is a testament to the precision and innovation of modern metallurgy. Next, these ingots are heated, forged, and sometimes alloyed with other elements like aluminum or vanadium, depending on their intended use. This step tailors the titanium's properties for everything from aerospace components to medical implants. The journey from raw element to engineered material is almost done. The titanium is now ready to be shaped into high-performance products that take advantage of its remarkable strength and lightness. But the story doesn't end here. Let's see how titanium gets even stronger and how it's transformed into the advanced materials that power our modern world. Pure titanium is great, but alloying makes it even better. By adding elements like aluminum and vanadium, we boost strength and heat resistance. The most common alloy, Ti6Al4V, is a favorite in aerospace for its strength and lightness. Alloying happens during melting. Elements are mixed with the sponge, then melted together. Precision is key, even small changes affect performance. The ingot is then forged or rolled into plates, bars, or sheets, building blocks for final parts. These forms are machined into everything from airplane wings to laptop cases. Each step is carefully controlled to maintain quality. From rough ingot to precision part, titanium's journey is all about engineering excellence. Shaping titanium is tough. Its strength and toughness make it hard to cut. Machining involves slow speeds, high feed rates, and constant cooling to manage heat. Special tools made from tungsten carbide or coated with titanium nitride are essential. Even so, tools wear out quickly, making machining costly and time-consuming. Engineers use techniques like near-net shape forging to reduce waste and effort. Every improvement helps make titanium more accessible. Machining is a critical, challenging step in creating high-performance parts. The result: precision components for demanding applications. Next, let's see where all this hard work pays off. Where does all this titanium go? Aerospace is a major destination. Jet engines, airframes, and landing gear rely on its strength and lightness. In medicine, titanium's biocompatibility makes it perfect for implants and surgical tools. It's also used in chemical processing, marine equipment, and high-end sports gear. Even consumer products like watches, eyeglass frames, and smartphones benefit from titanium's durability and style. While still a specialty material, its unique properties make it essential in advanced technology. From flight to healthcare, titanium makes a real difference. Its journey from ore to application is a story of science and innovation. Titanium truly is a metal that changes lives. Making titanium is energy-intensive, with a significant carbon footprint. Chlorine gas used in the process also poses environmental challenges. Recycling is key. Titanium can be reused endlessly with minimal energy. Melting down scrap saves resources and reduces impact. New methods like electrochemical extraction and 3D printing promise cleaner, more efficient production. Additive manufacturing reduces waste by building parts layer by layer. The industry is working toward a greener future through innovation and recycling. Balancing performance with sustainability is the next chapter for titanium. Titanium is more than a strong metal. It's a symbol of modern technology. Its unmatched properties enable lighter planes, durable implants, and corrosion-proof structures. The journey from mineral sand to high-tech alloy showcases human ingenuity. As demand grows, new production and manufacturing methods will make titanium more accessible and sustainable. Its story is just beginning, with endless possibilities ahead. From the depths of the earth to the heights of the sky, titanium shapes our world. Next time you see a jet or a medical implant, remember the science behind it. Titanium, the superhero metal powering our future.